The scissors linkage is subjected to a force of 150 newtons. Determine the angle theta for equilibrium. So theta is right there. The spring is unstretched at theta equals 0. Neglect the mass of the link. So if theta is 0, this is all collapsed into the pull. And as we pull it out, we're going to have P stretching in this direction. We could call that X. And then we're going to have the force of the spring stretching there. We call that Y. So we could say that P times X plus the force of the spring times Y is going to be 0. Now let's look at X. This distance is 0.3. So all these are 0.3. So these angles will all be the same. And this distance here, X, will be just 0.3 sine theta. So this is 3 times 0.3 sine theta, because there's 3 of those distances. Now Y here is going to be 2 times 0.3, and this time would be cosine theta. So P times 0.3 times 0.3 is 0.9, so 0.9 P sine theta for that one, and then Fs 0.6 cosine theta equals 0. Let's take the derivative now. So we have 0.9 P cosine theta d theta minus 0.6 F sine theta d theta equals 0. So d thetas cancel. Now we need Fs here, and we can put 150 in for P. So if we put 150 in for P, we get 135 cosine theta minus 0.6. Now Fs is going to be force of spring, force times the distance s. Now s is going to be this total length, because it's unstretched is 0. So the total length 0.6 minus whatever it's compressed. So 0.6 cosine theta. That is the stretch. So F is K times S. So K is 15,000 times S, the stretch, 0.6 minus 0.6 cosine theta, sine theta. And there we are. Now if we multiply this all through, we get 135 cosine theta minus 5,400 sine theta. That's this times that, plus 5,400 cosine theta sine theta. That's this times this times this. And we get this equation with sine and cosine in it. Put that in your graphing calculator, see where it crosses 0, and it's going to be at theta equals 20.9 degrees.